welcome back, and today we're going to be doing some trigonometry. I will say this is one of the harder chapters of AICE Math, but we'll get through this. There's two main things I'd say you need to know in this chapter. It's used in a lot of the questions. The first one is that sine over cosine equals tangent. That's one of your proofs. And the next one is that sine squared plus cosine squared equals 1. And also, cosine squared equals 1 minus sine squared. We get that from subtracting sine squared on both sides. And then sine squared equals 1 minus cosine squared as well. This can be found from the Pythagorean's theorem, where, let's say we have this is the axis, this is our unit circle. We have this line right here, that is our cosine line, so that's cosine. And we have the up direction, which is our sine, that makes the right angle. So this is the hypotenuse right here. The radius of the unit circle is 1, so that's how we get the equation that cosine squared plus sine squared equals 1, because it follows a squared plus b squared equals c squared, right? So with this identity proof in mind, and these ones as well, let's head right into it. So we have our first problem that given theta is an obtuse angle measured in radians, and that sine of theta is going to equal k, we need to find in terms of k. In terms of k, it seems pretty important. Basically, it means our final answer should have a decent amount of k in it, right? An expression for cosine theta, and we have some other things as well, but we'll focus on the first problem for now. So we have sine pretty much equals k. You can write theta every time. I don't, because it just gets messy at one point, but as long as your final answer has theta or x, whatever it is, you're fine. So sine equals k, and we need to get cosine. So what I want to think about first is how can we get sine and cosine to correlate somehow? We have our first thing, that sine over cosine equals tangent, but we don't have any tangent we're working with right now, right? So I wouldn't really use this one, but we also have sine squared plus cosine squared equals 1. So we know sine equals k, so we can plug that in. We can say k squared plus cosine squared equals 1. And now we just need to solve for cosine right there. So we need to subtract k squared on both sides, so we get cosine squared equals 1 minus k squared. Then since this is cosine squared, we need to square root both sides. This is a plus or minus square root, I should add. So cosine equals plus or minus 1 minus k squared. And we can figure out if this is a plus or a minus by using the phrase, there's a few out there. I use all seniors turn crazy. There's all students trust Cambridge. There's all seniors take calculus, whatever you'd like. Why is that not appearing? Oh no. Sorry, I'm having some really minor technical difficulties, but pretty much we have the phrase that all seniors turn crazy, all seniors take calculus, all students trust Cambridge. No, they don't, but we have ASTC, and it represents the quadrant, so go in a counterclockwise motion. That's really important. And what this represents is that all things are positive in the first quadrant. Not only sine is positive in this quadrant, only tangent is positive in the third quadrant. Then cosine right there, only cosine is positive in that quadrant, right? So, and the reason why tangent is positive right here is because it's sine over cosine, which we have negative sine, negative cosine. That's going to equal a positive tangent, right? And you can also connect this to how cosine is like the x values. Cosine is still going to be positive on that right side then, and our sine is like the y value, so it's going to be positive up above the x-axis and negative down below, right? You just need to memorize that ASTC is where all the things are positive, respectively. So we go to, we heard up here that theta is an obtuse angle. An obtuse angle is something that's greater than 90 but less than 180 degrees. So it's about right here, right? And it's notably in the sine quadrant, meaning it's positive, and we do see k is positive right there. And that means up in that sine quadrant, cosine is going to be negative. Because if you think about cosine's x value, it's going to be negative on that left side. So cosine of theta equals negative square root 1 minus k squared. And I'll just box in the answer right here. And we also have our next part, we're finding out tangent. So tangent is sine over cosine. And if we know sine equals k, and we know cosine equals all of this, then we can just toss them over each other. You can have k in the top, and cosine, which is negative square root 1 minus k squared, equals tangent of theta. And that is the final answer to put that together. If you think about it, we just got 2 marks from just putting those on top of each other. Like, if you look at the mark scheme, this is exactly what they want. They don't want you to do any form of math, which is a bit ridiculous, right? But it's nice, just get those 2 marks right there. Then we have part 3, which says sine of theta plus pi. We need to figure out what that is. So let's start thinking about how that would affect things. So if we're in radians, right, this is going to be 0. It's going to be pi over 2. It's going to be pi. And this is 3 pi over 2. And this is also 2 pi. That isn't a fraction, that's just saying either or, right? And previously, we're right up here. But if we're adding pi, that's pretty much going over here now. Because if you see, from here to there, it's about 180 degrees if you think about it normally. So if 180 equals pi, then that means going on a straight line over. If we add 180, we get over there now. So that means in this quadrant right here, cosine is positive, but sine is negative. So our final answer is going to be that sine of theta plus pi equals, I did that wrong. It equals negative k, and that is our answer. It is 1 mark right here, so you shouldn't be doing too much math, but also this requires a decent amount of brain power, so it's okay if you didn't get that, because the previous parts of our problem, we got 3 marks, and 3 marks out of 4 is still really, really good for this kind of chapter. I just cleared our work, that way we'd have more room, but remember the answer to the final one is right there, so we can always refer to it if we need to. This word hence right here, this word hence, I want to say means sort of like therefore, furthermore, using this information, because whenever you see hence, almost always you're plugging in your answer into there somehow. So even if you don't know how to do part I in this one, you can still do part II by using that tangent theta minus 1, etc., and plugging that in if you know how to do part 2. So you can still pick up those 4 marks even if you can't pick up the 1. So we're going to start this problem by setting those 2 equal to each other. Tangent theta minus 1 over tangent theta plus 1 equals tangent theta over 6. And if you think about it, using your answer in the previous one, it's also so much easier to work with in the sine cosine nonsense, because now we have only tangent. We like it when we have only one operation in there. It makes it so much easier for our lives, our calculator, etc. So when we have fractions, what we almost always want to do is to multiply by the denominator to make the fraction not a fraction anymore. For example, if we had 2/3, we multiply by 3, it would equal 2, right? So it just cancels out like that. So I'm going to start with the left. I'm going to start with the left. We're going to cancel out this tangent theta minus 1. Oh, plus 1 minus, my bad. So this is going to cancel out in this fraction, so we don't have to worry about the left side. But the right side still needs that to be multiplied. So we'd have tangent theta minus 1 equals tangent times tangent theta plus 1. Ideally, you're writing tangent every single time, but I personally don't do it all the time. The AICE examiners don't look at if you write theta every time, they just look at if you have the steps. And along with this, you can also say on the side, tangent of theta equals t, and just write t every single time. And we will switch to that later on in a different step. So tangent theta minus 1. But if you do use this equals t, your final answer must be reconverted into tangent of theta to show you still understand that. Get that final answer mark, So we're going to distribute this tan to both of these. So tangent theta squared plus tangent over, it's all over 6, my bad. So in order to get rid of the 6, we're going to multiply everything by 6. So 6 tangent theta minus 6. Absolutely remember to do that minus 6 at the end. That's absolutely crucial. So we'd have tangent theta squared, that canceled out. and then we'd have plus tan, like that. Now, if we start converting these tangent thetas into just t, we'll see a really interesting pattern here. Equals t squared plus t. We have t squared, we have this normal t. This almost looks like a quadratic. So with all quadratics, we start with setting it equal to 0. 0 equals t squared. We want to keep the number in front of t positive if we can. Just makes it easier to factor. Plus t minus 6t, and plus 6 at the end. So 0 equals t squared plus t minus 6t, that's going to be minus 5t plus 6. And now it looks exactly like a quadratic. We can factor, we can use a quadratic formula, we can do whatever we like. But I'm going to factor in this case. We need a number that adds into negative 5 and multiplies into positive 6. So because we need to multiply into a positive number, it's both positive or both negative. And since we need to add to a negative number, we know they're both negative. So multiplies into 6, there's 6 and 1, 3 and 2. I like 3 and 2, because if you add those together, it's negative 5. So we'd have t minus 3, t minus 2. So if we set those equal to 0, then we know that t is equal to 3 and t is equal to 2. That is not all of our answer, because t equals tangent theta, right? So this means that tangent theta equals 3, and tangent of theta equals 2, like that. So this is a step where you want to get your calculator out. We're going to put this to the side. We'll do one, that'll probably clear the screen, and do the other. So if we have tangent of theta equals 3, you can do either one first. I'm just doing the first one. We would take the inverse tangent on both sides, so theta equals inverse tangent of 3. The inverse tangent of 3, make sure you're in degrees for this question, as at the way top it says between 0 and 180. If it was between 0 or pi, 0 and 2 pi, then it'd be radians, right? But for this one, it's in degrees, so we get that theta equals 71.56. And for these degrees, it's actually a really big number in your calculator, but we would round to theta equals 71.6, like that. Because on the AICE exam you might write 5118 just to make sure that you have all your numbers there, but that is what we write. We have to remember, for all these trig functions, we always have 2 answers. So we have up here, all seniors turn crazy. 71.6, this is 0, this is 90, 180, 270, and 360. This is about right here. And I'm gonna give you a little secret. For tangent, you can just add 180 to your answer, or subtract 180 depending on what you have. So for this one, it would be right here. So we go across that line, and theta could also be 251.6 degrees, roundabout. And remember, our domain says it must be between 0 and 180. So this is not one of our answers. But I'd still recommend writing this step, that way the AICE examiners know you know how to find that extra answer. There's possibly a secret mark just from not having that answer there, right? And you never really know if that second answer will work until you really try that. So I'm going to erase some of our work right here, just to give a little extra room. And switch back to the pen. So our next one, right there, is that tangent of theta equals 2. So we take the inverse tangent on both sides, so theta is equal to the inverse tangent of 2. So the inverse tangent of 2, so theta is equal to 63.4 degrees, roundabout. We do 1 decimal point, 1 to 4 degrees. And then we look at our all seniors turn crazy. A is right there, 180 is down there. So plus 180 to our final answer. Theta could also be 243.4 degrees, but that is not in our domain, so it does not count. So our final answers are 63.4 and 71.6. So now question 3, express the equation 3 sine of theta equals cosine theta in the form of tan theta equals k, and solve the equation for 0. So this is pretty much our domain at the end. So we just need to keep that in mind in general. So express the equation this as this. So we know tangent is sine over cosine. So if we have sine on one side, cosine on the other, we can just divide by cosine on both sides. 3 sine of theta equals cosine of theta divided by cosine of theta. So cosine divided by cosine, that cancels out. Anything divided by itself is 1. We know trig looks weird, but it's not going to be equal to 0. That's a very common mistake people make. Because they think it's equal to 0, then they go through the rest of their equation, they think it's just 0. But it's not. So we have 3 tangent theta on the other side. And the reason why cosine divided by cosine would be 1 and not 0, everything divided by itself. So 2 divided by 2 equals 1. 15 divided by 15 equals 1. X divided by x also equals 1. So we just need to keep that in mind as we go through these kinds of questions. So, because now that we have this, if we had 0 on the other side, 0 divided by 3 would be 0. And that sort of messes up our work. So we want tangent by itself. So divide by 3 on both sides. Tangent theta equals 1 over 3. So this looks like a very easy, nice problem. Now we're going to take the inverse tangent on both sides. Theta equals tangent inverse of 1/3. And our question, the domain, is 0 to 180, so we have to make sure our calculator is in degrees at the moment. Inverse tangent 1 over 3. That would be equal to about 18.4 degrees. And I want to make a note here, the reason why we're doing this divide by 3 before the inverse tangent right there is because we work sort of outside to the in. We work in reverse PEMDAS order as well. So if we had an equation, for example, 3 cosine of 2x plus 1/2 plus 5, right? We would start with PEMDAS is PEMDAS. Please excuse my dear Aunt Sally. It's parentheses, exponent, multiplying and dividing, those two go together, and adding and subtracting, which go together. We would start with reverse PEMDAS, so we'd add or subtract our numbers. So we subtract on 5. Then we multiply or divide, so we divide by 3. Of course, the whole thing, I'm just writing little parts, that way you can still see the problem. Then we go to what's exponent. We don't really have any exponent, but we do have parentheses right here. So these exponent, I would almost say it's also an operator. So that's where you take your inverse cosine, right that. Then you're working in your parentheses. When you're in parentheses, you sort of restart. You start with adding and subtracting. We would subtract 1/2, and then we would go to multiplying and dividing. We would divide by 2, if that makes sense. You sort of work outside to your inverse to your inside the parentheses. You would reverse PEMDAS order every single time. This is going to be true for like every single problem we do here. And anyway, I got a little bit sidetracked with that, but I just want to make sure y'all understand that little segment. So we have our answer, theta equals 18.4. But we also have to consider if there's a second answer that we can write. So all seniors turn crazy. We took the theta of something positive, so it's going to be an all quadrant and the tangent quadrant, the first and the third. So we take 18.4, we'd add 180. So theta could also equal 198.4 degrees, but our domain is from 0 to 180, so we could not write that answer. Alright, so now it's time for part 2 of this question. We need to solve the equation 3 sine squared of 2x equals cosine squared 2x for that the domain is between 0 and 180. That's always important for our final answer, but in the middle, I wouldn't say it's too significant. It's only like you got your final answers, you should look at it again, right? Because that's a really easy way to get the extra mark for knowing what is an answer and what isn't. So the equation 3 sine squared 2x equals cosine squared 2x. So we have our one proof that sine squared plus cosine squared equals 1. And a really good hint that we're going to use this is because we have both squared items in right here. Even just having one squared item could be a really good hint for that. And we have 2 different operations. If we don't like 2 different operations, it's almost like having 2 variables in one equation. We can't solve it unless we use discriminant or something else, but we can't use discriminant in these kinds of general equations. So we want just one kind of variable, one kind of operation we can use. So you can choose to get rid of sine, get rid of cosine. I'm going to get rid of cosine in this case because I just feel like it, but either way works. So we'd have 3 sine squared of 2x equals, so we get cosine squared by itself by subtracting sine squared on both sides. We get 1 minus sine squared. So we're going to plug that in right there. Because remember, this is still sine squared of theta, and 2x is sort of our theta in this case. So we do 1 minus sine squared of 2x. It's always good to put in parentheses whenever you first put it in, just make sure there's no things you have to distribute, like a negative sign, something really simple like that. So we have 3 squared theta. I'm just going to remove the parentheses because we don't need it in this case. 2x. So now we have only one operation. We just want to get sine by itself. And this is a little bit messy. I would start with adding the sine squared 2x to both sides. So we have 3 sine squared, and we have 1 sine squared like that, so we can combine them for 4 sine squared 2x equals 1. Now we can work outside towards inside. We can divide by 4 on both sides. So sine squared of 2x equals 1 over 4. Now, this is where a lot of people get confused. They start dividing the 2, but that's not what we're supposed to do. We see the sine squared. So we have to take the square root on both sides, the positive or negative square root. So we have sine of 2x equals the positive or negative square root of 1 over 4. With these kinds of questions, what I prefer to do is separate these into the sine 2x equals positive 1 over 4, square root, and sine of 2x equals the negative square root of 1 over 4. And the square root of 1 over 4, we take the square root of the numerator and the denominator. So the square root of 1 is 1, and the square root of 4 is 2. So we can just make this a bit simpler and write that out. So we'd have positive 1 over 2, and sine 2x would be negative 1 over 2 like that. So now that we have our sine by itself, we can take the inverse operation. I'm just going to move our work sort of over here. We'd have 2x equals the inverse sine of 1 over 2. And we're supposed to be in degrees for this problem. Make sure you know that. So inverse sine of 1 over 2, 1 over 2 in your calculator is 30. So 2x equals 30. And if we divide by 2 on both sides, x equals 15 degrees. But also, we need to find our second answer for this, because every single operation is going to have a second answer. Even though if we have 2 operations going at the same time, that just means 4 potential answers, assuming it correlates with our domain. So we'd have I'll do it on the left side. All seniors turn crazy. We know, the thing is, we don't always use our final answer when we're doing this angle comparison, I want to say. We would use whatever we took the inverse of like that. So we would take 30 degrees, not the 15, because we divided by 2. Because later on, that's when you divide by 2. 30 is right here. 0, 90, 180. And it was a sine, and we took it of a positive number, so it would be around over here. So we do 1/8, I want to say 30 minus 0, we know that's 30 right there. In order to get that angle that matches, we do 30 right there. So 180 minus 30 would be 150. So we'd also have 2x equals 150 degrees. And then divided by 2, x equals, let me divide by 2 in my calculator, 75 degrees. And those both correspond with our domain. They're both less than 180. And now our second part, we had sine of 2x equals negative 1/2. We're going to start with doing the inverse sine on both sides. So I'll make a little line like that. So 2x equals sine inverse negative 1 over 2. So get that in your calculator, negative 1 over 2. Make sure to include that negative, that's very important, this one. So 2x equals negative 30. And then we can get x and divide that by 2. So x is negative 15. The thing is, our domain is between 0 and 180, so a negative number would not be able to apply. We can try to convert this. We can make this 15 into, pretty much you do negative 15 plus 360, a full unit circle, and you would get 345. Or you get negative 30, add 360, which is 330. Oh. Okay, so I think what I would recommend is then turning that negative into that normalish looking number and then divide it by 2. I think that's more of a correct solution. So we divide this by 2, 330 divided by 2 is 165. That's probably a really common mistake that the AICE examiners want you to make. So keep that in mind, that you change it to a negative into a positive before dividing, because it will sort of mess up your number from there. See, I didn't know that, so I probably wouldn't get that 1 mark if I was going through this exam. But also, we need to get our second possible answer. So we have inverse sine of negative 1/2. And we got negative 30 from that, or our positive 330. I'm going to use positive 330 because our unit circle goes based on positive numbers. So that's 0, that's 360, and 330 is around right there. We took sine of a negative number, so it's going to be where sine is negative. That's a very common mistake students make, that they want to automatically go into the A, automatically go into the S, but we need to go into T, where sine is still negative. So we always go based on the x-axis when we're finding our differences. We saw in the first one we took 30 from the 0 and 30 from 180. We would never go to 270. It's a really common mistake. You would just mess up the problem, right? So just always go from the x-axis. So right there, we have 360 minus 330 would be 30. And 180 plus 30 would be 210. And 210 does not correlate with our domain right now, but we would do 2x equals 210, divide by 2 on both sides, calculator time. That'd be 105 degrees. So remember, when you get your answers for these, you have your first angle, then you have your second angle. Always remember to still go on with your operations, whether it be subtracting, dividing, multiplying, whatever, because it's very important to see if your final answer will correspond with your domain, you know? So for this question, we have 4 answers. I think when I was looking at the mark scheme, it said to get 1 answer, you get 1 mark, but to get all of the answers, you get another mark. So it's not a mark per answer, because we did a lot of work here. But I think it's 2 marks for the work. You get 1 answer mark right there. It could be for any of them, and there's 1 answer mark for the 3. So it's no worries if you don't get one, you'll still have an answer mark for getting one of your answers. Okie dokie, now question 4. We need to find the value of x satisfying the equation the inverse sine of x minus 1 is equal to the inverse tangent of 3. Okay, we have 2 operations here. We want to see if we can limit that to just 1 operation, whether it be sine or tangent. Now I notice here, inverse tangent of 3, that's just a number, right? So we do inverse tangent of 3 in our calculators. It doesn't say radians or degrees. I'm more used to degrees, so I'm going to do degrees for this question. So the inverse sine of x minus 1 equals 71.6 degrees roundabout. In our calculations, we're going to be using the full number, but for the AICE exam, you just write down those 3 sig figs. That's going to work perfectly. So now we'll take the sine of both sides, because if the inverse sine is going to cancel out sine, then sine will cancel out inverse sine. It's almost like if you have a square root of x, you can square that to cancel out, or if you have a square root the x squared, you can square root that to cancel it out. It's just sort of like the same practice, right? So we have x minus 1 equals sine of 71.6. So let me get sine 71.6. We're using the full number in our calculator, which is 71.56, etc., etc. So we get x minus 1 equals 0.9. It's 4, 8, 6, 8, etc., but for degrees, we always go to 1 decimal point. So then we add 1 on both sides. So this would be 1.9 degrees. Just like that, 3 marks. And now we have problem 5 to solve the equation 13 sine squared of theta over 2 plus cosine theta plus cosine theta equals 2 for our domain being in degrees. I'm still in eraser mode. For between 0 degrees and 180 degrees. So there's 2 things we can do here. We can make it so we have only one operation first, or we can get rid of this fraction. I'm going to start with getting rid of the fraction, and with hindsight, this is a lot of operations, right? We have sine, cosine, cosine. I don't want to write that out every single time, so I'm just going to make a note. Sine, the s equals sine of theta, and c equals cosine of theta. That's just sort of for the examiners if I was taking the exam. I don't think you have to do that. I think they would get you, but it doesn't hurt just to make that little key. You know, it takes a second versus the many seconds you're saving from using the shortcut. So we have 13s squared over 2 plus c equals 2. I'm going to start with multiplying by 2 plus c on both sides. So this would cancel out in the denominator. So we just have 13s squared. We need to distribute that to that c in the middle. So plus c times 2 plus c, and distribute that to the 2 right at the end. 2 times 2 plus c. I will distribute in a second, but now I'm seeing I'm going to have a lot of c's in this equation. So s squared is probably what I should be getting rid of. And we know s squared, well, sine squared plus cosine squared equals 1. So if we subtract sine squared on both sides, cosine squared. No, my bad. We need to solve for sine squared because that's what we're trying to get rid of. So 1 minus cosine squared. So we're going to take this entire thing and plug it in for sine squared. So 13 times 1 minus cosine squared. I should have written c. Whatever, it's fine. We know what I'm doing. And I'm just rewriting what I just wrote up above. That way I can distribute in one full step and then get everything on one side and the next. So 13 needs to go to both of those things. We'd have times 1, which is 13. Then we'd have times a negative number, which is just going to be negative 13c. Then distribute c to both these items. We'd have plus 2c, then plus c squared. Then we're going to have that equal to all these distributed. So 2 times 2 is 4. 2 times c is 2c. And now we see we have a c squared, so it's going to look like a quadratic when we get it all on one side. So we're going to start doing that. I'm going to put c squared first. We don't have any c squared, so I don't have to worry about that. We have plus 2c. I'm going to subtract 2c on both sides, minus 2c. And then we have a minus 13c as well on right this side. We have plus 13, and we'd have minus 4 when we subtract 4 on both sides. Equals 0. Now we're going to make this look a bit nicer. We have c squared plus 2c minus 2c. That cancels out. So we'd have negative 13c plus 13 minus 4. That's going to be plus 9 equals 0. And now we have our quadratic. So let's look into how to factor this. I know we need to make something that adds into 13 but multiplies into 9. So there's 9 and 1, there's 3 and 3. Is there anything else? Let's try doing polysolve on this. We'd have 1 as A. We'd have negative 13 as B. And C is 9. It does not give us a very clear number. Okay, I just looked at it for a second. I made a mistake. That's so easy to make. So easy to make. And perhaps y'all caught it a bit earlier. When you distribute your 13 and this beginning part right here, 13 times cosine squared is going to be 13 cosine squared. So that little bit just messed me up. So we have cosine squared. So c minus 13c squared would be negative 12 squared, c squared, plus 9 equals 0. So that's the reason why I was having some difficulty factoring, is because I could not factor what I was doing. So I would start with dividing by 3 on both sides. That seems to be a common number. 0 divided by 3 is 0, so it just makes the thing look a bit nicer, but you don't have to do it at all. And now we just want to get c by itself so we can start doing our cosine stuff. So I want to subtract 3 on both sides first. That'd be negative 3. I want to divide by 4 on both sides, so c squared is going to equal 3 over 4. So make a little segment here. C equals the positive and negative square root of 3 over 4. And now we can separate this into, is it desync? No! Alright, I got it to resync again. We have the positive or negative square root of 3 over 4. So we know that one of our answers, well, not one of our answers, one of our intermediate steps is that cosine of theta is equal to the square root of 3 over 4, or, well, slash and, the cosine of theta equals negative 3 over 4, like that. So now it's just time to take the inverse cosine and then get our two answers, then box in our answers, right? So theta equals cosine negative 1, or the inverse cosine, of the square root of 3 over 4. So we're going to start plugging that into our calculator. That the inverse cosine is equal to the square root. Make sure you put the square root over the entire fraction, not just the numerator. So that gives me 30. So theta equals 30. And whenever you get these answers, I recommend you recheck your domain. Make sure you're supposed to be working in degrees, radians, etc. For right now, we're in degrees, and that's very good. And now we can start working on our two answers. All seniors turn crazy. 30 degrees is in this quadrant right there, between 0 and 90. And we know our other answer. Since cosine is positive, we would put it back down there where cosine is positive. So it's 30 degrees between 0 and 90. So it's going to be 30 degrees from 36 and our new angle. So we would do 360 minus 30, which theta equals 330 degrees, which we know does not fit into our domain, so we cross that out. And we box in the one that does work. Our next one is when it's a negative square root. So we take the inverse cosine both sides. So I should write that out. Inverse cosine, negative square root. So pretty much it's just what we did previously, but with that negative sign in there. So 3 over 4. So theta equals 150 degrees. So I prefer to draw a new one a new little graph every time I do this, that way I don't confuse my angles at all. So we know this is 0, 90, 180, so 150 is between 90 and 180, so it's about right here. It doesn't have to be super accurate, just enough to know the quadrant. So we see that's where sine is positive, and that's true because our cosine is a negative value, the negative square root. So we know that our other value would be in this tangent quadrant. So this is a 150, so we do 80 minus 150, that equals 30. So between this and this would be 30 degrees. 180 plus 30 is 210, which does not fit into our domain. So we can write it out. Theta can also be 210, but it's not an answer. We'd only have the two here, which is 30 and 150. And I want to add, a lot of times you can have a decent amount of intuition of what will fit into the domain and what won't. For example, if you just know that your next one's going to be in quadrant 3, which is beyond 180 degrees, you don't necessarily have to find the number, but I find it just be useful. You know, it's a nice habit to have because worst case scenario, you spend a few extra seconds doing it, you know? But if you have that intuition of what fits and what doesn't, feel free to skip that canceling out step. I would just really recommend doing it every time. I would personally do it every single time. Even though I'm pretty solid at math, I would double check my work. It's always really good to double check. So we have our next question. We need to show that the equation 1 plus sine x tangent x equals 5 cosine x. How it can be expressed as 6 cosine squared minus cosine x minus 1 equals 0. Alright, so we have sine, tangent, cosine. It's all very, very messy. So I'm just going to see if I can get rid of even one of these and try to go from there. 1 plus sine x tangent x equals 5 cosine of x. So one thing I do know is that sine over cosine is going to equal tangent. And I think for now I'm just going to switch over to letter mode. That way everything looks a bit more in like algebra rather than pre-calc. So 1 plus st equals 5c. That looks so much neater to write. And if we know that t equals s over c, we can plug that in. So s would be s times s over c, like that, equals 5c. We're already one operation down. We only have 2 operations left in this, which shows me this problem is pretty doable, despite looking sort of scary in the first place. So we know s times s would be s squared over c equals 5c. Now, we also know that sine squared plus cosine squared equals 1, right? And we have sine squared right here, and you want only cosine. So sine squared equals 1 minus cosine squared, because we subtract cosine squared on both sides. So 1 plus 1 minus cosine squared. I was supposed to write c. I'm so bad at being consistent, but it's fine. It also helps just write that you can switch back and forth between just letters and full thing. AICE examiners won't really mind too much. So now we have that. What I would do is get rid of this pesky fraction. We don't really like fractions too much. So we're going to multiply all this by c. So 1 times c would be c. That fraction cancels out, so we have 1 minus cosine squared. Then we'd multiply the c times c, which is 5c squared. So now that we're here, we sort of see how it starts to look like a quadratic a little bit. I'm just going to rewrite this one step so I stop messing up. And we're going to make this all equal to 0, like you would with any quadratic. We're going to add c squared both sides. That way we have a positive c squared number. We would subtract c on both sides, subtract 1 on both sides. And that is our quadratic we're dealing with. So, trying to think about how to factor this one. I'll just polysolve it in my calculator. Because if you do have any kind of polysolve function or thing that can automatically factor, automatically do the quadratic formula, I very much recommend using that kind of calculator. I use the TI-36X Pro if that helps anyone. And we get 3x minus 1 times 2x. Wait, that would be a plus 1 right there. And that would be a minus 1 right there. If we want to, we could factor this out again, make sure that goes into what we want. So 6x squared. We do the outside, which is 5. That'd be, well, first outside, we would do negative 3x. Then the inside numbers is plus 2x, which equals negative 1x. I'm writing x, but I should be writing c. That's such an important thing that everyone needs to know. You need to write c, you need to write c, you need to write whatever you're writing. Because AICE examiners might think x, oh, you're saying your final answer, but you aren't. And it's such a bad thing. I know a lot of people that do it. That'd be negative 1 at the end, so we have 6x minus 1x minus 1, right? So now we can just set these operations equal to 0 and solve for c and not x. Even if it's really tempting to write x. So we have c equals negative 1/3, and c equals 1/2, right? So we're going to write our work over here. It would be cosine of x is equal to negative 1/3. There's no domain for this question, I was just double checking that. So we don't have to worry about degrees, radians, we're all good for everything. So cosine of x, we need to take the inverse cosine both sides. Negative 1/3, that's really important. That determines what quadrant it's in. So the inverse cosine of negative 1/3. X is equal to 109.5 degrees. And we need to do our all seniors turn crazy. And 109.5 is going to be right there between 90 and 180. And we're going to put it in this other tangent, this other quadrant as well, because the all quadrant and the cosine quadrant is where cosine is positive and cosine is negative in this case. Even if our degree number is positive, it is a negative number we're taking the cosine of, if that makes sense. So we do 180 minus 109.5. Use the full number in your calculator as always. And we're going to do 180 plus that number. So x equals 250.5 degrees roundabout. So that's 2 of our answers. But then we have our other thing of cosine, where cosine of x equals 1/2. So we take the inverse cosine both sides. So inverse cosine of 1/2 is 60 degrees. So we have all seniors turn crazy. 60 right there between our 0 and 90. And since cosine is a positive number, it would then go in the fourth quadrant right there. So it's 60 degrees between 0 and our angle, 60 degrees. So it's going to be 60 degrees between here and here. It's 360, so we do 360 minus 60, which equals 300, if I can write that out. And those are our other 2 answers for this question. Okay, bro, I just realized, when I was planning out this video, I made the same mistake as I did just now. Part I only wants you to show that 6c squared minus cosine x minus 1 equals 0. And we did that right here, right? And then the next part is where it says to solve the equation for that. But it also says that's where our domain comes in. So my bad, I started doing a lot of 6ii. I got most of the marks. And since our domain is between 0 and 180, we would just cross out all the answers that are below 0 or above 180. So that'd be the 250, and that'd be the 300. So our answers are 109.5 and 60 degrees. Now we have question 7 to show that sine to the 4th power of theta minus cosine to the 4th power of theta equals, or is absolutely equal to, 2 sine squared theta minus 1. Alright, so I'm just going to start writing this out with sine being s and cosine being c. So s to the 4th power minus c to the 4th power. I want it to look like 2 sine squared. So this tells me that I need to get rid of this cosine, and I also need to have only squared values while I have to the 4th. Now if you remember, there's a thing called difference of squares when we have factoring. An example of this could be x squared minus 9, where this could break into x minus 3 and x plus 3. And when you multiply this out, you would get x squared, so that's the first, the outside, plus 3x, inside minus 3x. The negative 3 times positive 3 would be negative 9. Those cancel out, and we get x squared minus 9. And this is essentially the same concept. We're just not dealing with squares, we're dealing with things to the 4th power, which x squared equals x to the power 4th, because when we have an exponent raised by an exponent, we multiply them. So this breaks into s squared minus c squared times s squared plus c squared, right? And if we know we don't want cosine at all in our answer, we need to replace this cosine squared with something. And the fact that we're doing a lot of squares might hint to you that we're going to be using the identity that sine squared plus cosine squared equals 1. So if we want cosine to be one that's replaced, you put cosine right there, and we subtract sine squared on both sides. So we take all of this, and we write out something that's going to be really messy, but we'll clean it up in a second. We have sine squared minus parentheses, that's very important, 1 minus sine squared. We have an end parentheses for our first set. Then we have our sine squared plus 1 minus sine squared. And the reason why parentheses are so important here is because for one of our little sets of I want to say an equation, but one of our sets, we have a minus sign that needs to be distributed to the whole thing. While on the other hand, the other has a plus sign that doesn't really get distributed. So it's really important to remember what's distributed and what isn't. If you ever in doubt, always plug in your things with parentheses. It doesn't hurt at all. So we have s squared minus 1 plus sine squared. I should have written as an s. It's fine, it's fine. Then we have s squared plus 1 minus s squared. So we'd have s squared plus s squared, which is 2s squared minus 1. Then we have s squared minus s squared, which cancels out. So we just have plus 1. And anything multiplied by 1 is itself, right? 2 times 2 times 1 is 2. 15 times 1 is 15. X times 1 is 1. 2 sine squared of theta minus 1. All that times 1 is going to be equal to 1 itself, right? So we can pretty much get rid of that and write out our final answer at 2 sine squared theta minus 1. And that's how we went from our left-hand side right there to our right-hand side. And then we have the second part of our question that says, hence, which we know means like pretty much using the answer that we gave you previously, which is the 2 sine squared theta minus 1. Solve the equation that all of this, which is our answer we're going to plug in right there, equals 1/2 for this domain. So it's pretty much a normal problem if you think about it. We have 2 sine squared theta minus 1 equals 1/2. And this is where we start doing our reverse PEMDAS, getting 2 answers. I'm surprised this question is 4 marks, but oh well, we'll work with it. I'm happy it's 4 marks. So we start with doing plus 1 on both sides. So 2 sine squared theta equals 1/2 plus 1, which is 3/2. Then we divide by 2 on both sides. Sine squared of theta equals 3/4. Then we do inverse sine on both sides. So theta equals... Oh, my bad. A very common mistake people do is that they'll take inverse before doing the square root. And I mentioned that earlier, but it's such a common mistake, even I do it all the time. So we have to take the square root on both sides, and that's a positive or negative square root. We have to remember that. So we'd have sine of theta equals the square root of 3/4. We had a question just like this. That's so weird. But also, the sine of theta equals negative 3/4. So we're going to take the inverse sine on both sides. So that's going to be written out like this. You technically don't have to put this parentheses. I'm just used to it. It might be an American versus British writing. I'm not sure. But regardless, anyway is correct. AICE won't get at you for just writing it slightly differently, as long as you still get the main ideas, like the plus or minus, for example. So we'll start with our left side for the inverse sine of the square root of 3/4. Yet again, make sure the square root covers everything, not just numerator. And that gives us 60. And all seniors turn crazy. Our 60 is right here. We're taking sine of this, so our next answer is going to be over here. We're going to say how we're 60 away from the x-axis right there. So we're going to 60 away right there. Then 180 minus 60 is going to be equal to 130, right? Is that right? That doesn't feel right. It is 120. I'm good at math, I promise. So theta equals 120 degrees. So that's 2 of our answers. And for this, the domain is between 0 and 360. So a lot of our answers are going to be pretty good for this one. That's not to 180 like we've seen a lot of them been. So next we need to do the right side, which is the inverse of sine, equals the negative square root of 3/4. And also, one important note, when you're putting this into the calculator, make sure you're never putting the negative sign inside the square root for when it's exactly like this. Because when you take the square root, let's say we're taking square root of 4, negative 4, like negative square root 4 like that, then we'd be negative 2 as your final answer. But on the other hand, if you have the square root of negative 4, that's going to equal to I. And the reason is because I equals the square root of negative 1. And you never want to AICE examiners, you never want to show them, hey, I got an imaginary answer when you aren't supposed to get that, right? So it's very important to make sure you put it in the calculator exactly how you wrote it on the paper. So, that tangent aside, theta equals negative 60 degrees. And we can't have a negative number. Our domain says it must be between 0 and 360. So, this means that we have to change this. And the way to change it is by adding 360. So negative 60 plus 360 equals 300. So that is one of our answers. And then we have our all seniors turn crazy. We have 300s in the last quadrant because it's between 270 and 360, like that. And that is true because we're taking the sign of a negative number, so it's going to be in that negative area. So our next one's going to be in this tangent in the third quadrant. So we're 60 we're 60 degrees away from the x-axis to the 360, right? So that means we're 60 away from 180. So 180 plus 60. If we did minus 60, I'd be going upwards. As you notice, we're getting less as we go up. This is like 90 over here. So 180 plus 60 equals 240. So theta equals 240 degrees. And those are our answers. And now we've got question 8, which is the graph question. I love graph questions. I'm a very visual person, not a very Englishy person, so when we have a picture drawn for us, I find it to be so nice. And we see that this diagram shows part of the graph y equals a plus b sine of x. State the values of the constants of a and b. This is 2 marks, so one's for a, one's for b. This shouldn't be too much work. This looks like just looking at the graph for the most part. But first we have to understand what a and b would do in this case. In general, when we have sine, it'd be drawn out with 1 and -1 sine of x, my bad. We would start at 0. I'm drawing those. These are 1/2 pi, 3/2, etc. I'm not going to write the words, just, it's the same one as the graph above. So we're starting at 0. We go up to -1. We go down back to 0. We go to -1, and we go back to 0. Then that's one period. It would pretty much loop from there. But on the other hand, if we have 3 sine of x, then that means we're going up to 3 and down to -3. And this is because, let's say you have y equals 3x. It's pretty much that same idea, where you're plugging in the same x value, but getting a number that's 3 times as big. So it would start at 0, just like normal, because 0 times 0 times 3 is 0. So start making our little notches. And we would normally go up to 1, but 1 times 3 is 3, so we'd go up like this. We'd go back down to 0, just like usual. Then we'd go back down to -3, as -1 times 3 is -3. So that's how our graph would look. It goes a bit more up, a bit more down. Then we have A right there, which is a horizontal shift. So let's draw another graph. Let's say we'll stick with our 3 pattern just to show you how the same number can work in different ways. So sine of x, it could be +3 in the front or +3 in the back. Either way, it makes the same difference. So let's say this goes up to make our little numbers here. We would have 4, 3, 2, 1. I don't know why this little thing appeared. I'm going to get away 1 second. Okay, it went away on its own. There we go. Let's just get back to the problem. So what this +3 means is that we're just moving upwards. So imagine we have y equals x plus 3. So when x is 0, what is y going to be? So y equals 0 plus 3. Y is going to be equal to 3. So it's going to start at this 3 mark. And, well, it's not going to start there. Yes, it would. Okay, I'm sorry. I'm trying to phrase this in a way that so it doesn't look like cosine. And then we have this number right here. It's 1 sine of x, so it'd go up to 4, right? Because in this previous one, we start at 0, we go up to 1. And now if sine is going to this first notch, it typically go up to 1, so we have 1 plus 3, which equals 4. That's how the graph works. It's the same thing as our previous one, but it's scaled up. Not our previous one as in 3 sine of x, but as in the original graph. We have our notch, notch, notch. We would go back down to 3. Then we go to 2, because typically we'd go down to -1, but -1 plus 3 is 2. That's how we get that. Then we go back up to 0 and start from there. So, in a way, we have 0 as right here. This time our 0 is like right here. It's given to be at the 3. So now that we understand like how all these shifts and stretches work, in case you're wondering, the 3 sine of x, that's called a vertical stretch of 3 when you have that, and it's only a horizontal stretch when it's with the x. So if we had 2x plus 4, like that in parentheses, then that would be considered our horizontal. But right now we're only doing vertical things. So I want to look at where our graph starts, because where our graph starts is a pretty good indication of what our shift upwards is. We see when we have plus 3, we start at 3, right? And I see with this one, we start at 1. So that gives me a really good sign that a equals 1. So, knowing this, let's draw our little line right here. So that's where 0 is. We go up 1, 2. So b equals 2. Of course, you're on AICE exam, you're not going to, I imagine you wouldn't draw all these little graphs, all that kind of stuff. So this problem did take longer in the video, but that's pretty much how you would go through all of the steps if you forgot. And in addition, you can plug this into your calculator and double check yourself. So for example, if you want to plug in it would be 1 plus 2 sine of x. And if you plugged in 1/2 pi for x, you should get negative 3. You should always get negative 3. If you don't, that's a sign you did something wrong. Now, what you do from there, I'm not sure. But you can also, low-key, you could try random numbers until one of them works. You have 2 marks. None of them is a work done mark. All of them are just, did you get the answer mark? So 1 plus 2 sine x is our answer. Okay, so question 9. Prove the identity sine of theta over 1 minus cosine theta minus sine theta is absolutely equal to 1 tangent theta. So the first thing I see, that there's a lot of fractions in this, and we see we have our first answer in 2 fractions and our final answer in 1 fraction. So that gives me a really good hint that we need to combine these fractions. The way you combine fractions, you see we have 2 over 3 and 5 over 7, right? And we need to subtract them because the question is subtracting. The way we would do this is by multiplying what's on the other side's denominator. And we multiply that in this way, where it's 7 over 7, or sine over sine, whatever. Because 7 divided by 7, anything divided by itself is equal to 1. So we're multiplying this by 1, so nothing is changing. And it'd be the same with this side, where we multiply by 3 over 3. We'd get 14 over 21 minus 15 over 21, which equals negative 1 over 21. That's how you would do it, because from there we have an intermediate step where we do 14 minus 15 over 21. That's how you subtract fractions. And in this question, that is essentially what we're doing in the same way. It's just with a lot more letters involved. So we're going to make these sines, cosines, make them simple letters. We're going to make a sine, then s, minus our c, minus 1 over s. And I'm not going to write as absolutely equal to 1 over tangent, because we're not supposed to do anything with that right side. We're only supposed to focus on the left and make it look like the right. You know, there's nothing we're supposed to do there. And that's a really good sign. Whenever it has this, it's hard to see on this screen, but when it has an equal sign with 3 lines, that means don't touch the right side, right? So we're going to multiply s over 1 minus c times s over s, because that's one on the other side's denominator. And for this one, we're going to multiply by 1 minus cosine, minus 1 minus cosine, just like that. So sine times sine is sine squared. Sine times 1 is sine. Sine times cosine. You know what? I don't like having that much s. I'm going to just make it 1 minus c times s. You can do that for the time being. If we need to distribute later, we'll distribute later. And I just think it will make it easier to work with for the time being. So 1 minus c times 1 is 1 minus c. Anything times 1 is equal to itself. Now we're going to do the same thing we did with the last denominator. We're going to make 1 minus c, then times s, just like that. And now we can combine these fractions. 1 minus cosine. And we have sine right there. So we know tangent is sine over cosine, right? Sine over cosine equals tangent. And tangent by itself is always over 1. Like, you know, every normal number you see is like over 1. So if our final answer is 1 over tangent, what this means is that we need to get cosine over sine. Does that make, you see where that connects? Because we have cosine connected right there, sine and tan connected right there. So that's pretty much where we're connecting them. We're switching it up, you know. It's like taking the -1 exponent on both sides. You have x -1, that would equal 1 over x. It's pretty much what we're doing, you know. If you do it to both sides, it's equal. So for our final answer, we want cosine in the numerator and sine in the denominator. So for this equation, we have in our numerator, we have sine r1 and cosine. So we want to make the sine into cosine. We see it squared. By now we know that sine squared plus cosine squared equals 1. So we can subtract cosine of squared on both sides, get sine squared minus, I can't English anymore. You say the same things over and over. But that's the math version right there, boxed in. So we would do 1 minus cosine squared minus 1 minus cosine. And we would do 1 minus c times s still on the bottom. And I think we're going to simplify the numerator. I think that sounds like a good plan. So 1 minus 1, that would just cancel out, so 0. And we would have minus cosine squared, then minus cosine on the numerator. 1 minus c times s, make sure to keep that denominator. So if we know we want cosine over sine, and we see sine in the denominator right now, we also see 1 minus cosine in the denominator. So we need to figure out how to make that cancel out. And my best idea at that is making the numerator have that. Because if we have 6x over 3x, right? Oh, that's a bad example because that divides evenly. 6x over 4x, right? You could cancel out x because they're both in the numerator. So we have 6 over 4. Then we say, oh, they both have 2, so we could do 3 over 2, right? So if we have 1 minus cosine in the numerator, we could cancel it out in the denominator. And I'm seeing cosine squared, oh, I didn't mean to write the whole word. And we've seen this minus cosine. This looks really similar to a lot of quadratics we used to see, where it'd be like x squared minus x. And we could factor out the x to get x minus 1. And it's the exact same scenario right here. We would factor out a cosine. So cosine, negative cosine squared divided by cosine would be negative cosine. And cosine divided by this negative cosine is going to be -1. Wow, it's taking a lot of time for my brain to think. Alright, so I think, because I was thinking through this for a second. If we have negative cosine minus 1, that doesn't look like our 1 minus cosine. If we rearrange it, it would be -1 minus cosine. So it's a very common mistake. It's very simple. Where this 1 minus cosine was in parentheses, and I did not remember to distribute that. So whenever you have a mistake, just make sure, go back through, check what you've done, because there's very invisible parentheses. That's why it's always good to have parentheses around what you insert, but also maybe around what you have already. So we have -1, then minus a negative cosine, which would be plus cosine, like that. So we have a plus 1 right there, because positive cosine divided by positive cosine is going to be equal to 1. Anything divided by itself is equal to 1. And then we'd have 1 minus c times s. And if we just rearrange this, this is equal to c, then 1 minus c over 1 minus c times s. So 1 minus c is going to cancel out, so we'd have cosine over sine as our final answer. And you can show them one final thing. I'm running out of room, but we have cosine over sine equals 1 over tangent. I would recommend writing that one final step, and that is your final answer. Nice, we're on to our final question. So we have 10, which is the reflex angle theta is such that cosine of theta equals k, where it's between 0 and 1. So we need to find the expression in terms of k for sine and tangent. This looks really similar to our previous question we had. I think it was the first question we had. But this time, instead of having an obtuse angle, we have a reflex angle. So this is where you need to know some math vocabulary. While an obtuse angle is something that's greater than 90 and less than 180, a reflex angle is greater than 180. So their axis like this, it would be in the T or the C quadrant. We're not sure which, but I'm just going to guess T for now. So all senior string case, that's where I'm getting the word T from, or the third quadrant if we want to be more formal. So we find an expression in terms of K that sine is that. So my main guess, like the first problem, is going to be having an equation that has both sine and cosine in it, which is sine squared plus cosine squared equals 1. And we have sine squared right here, and we have cosine in our main thing. So if cosine is equal to k, then we can just input k right there and square it. So plus sine squared, and it's pretty much the exact same problem. It's just, I think the only part that would trip you out is that's a reflex angle, and some people don't know what that vocabulary is. So we want to find sine. So we're going to subtract k squared on both sides. So sine squared equals 1 minus k squared. We're going to take the square root on both sides, positive or negative for the time being. 1 minus k squared. Now, in this quadrant, or the fourth quadrant, depending on where the reflex angle is, we know that sine is always going to be negative. We know this because sine is only positive in these upper two quadrants, because sine is your y value. So if we draw an xy graph, this is 1, 2, 3, etc., -1, -2, -3, and 1. I guess I'm committed to this now. 1, 2, 3, -1, -2, and -3. We see the the y is positive up here, and it's negative down here. So knowing that a reflex angle, it's greater than 180 and less than 360, so it must be in this lower quadrant. My whole thing just looks like scribbles now, but we see that sine will be equal to -1 minus k squared. If you don't understand the positive versus negative, that's okay. This question is 2 marks. One is most likely from getting this answer, and the next is probably choosing that negative. So you only lose 1 mark, and 1 mark isn't your make it or break it, right? Especially when you have so many other questions on AICE exam, so many other chapters. And our next one is to find tangent. Well, tangent is equal to sine over cosine. So we'd have sine as 1 minus k squared, like that, over cosine, which was k. And that is our final answer for tangent. And now for our final part, we need to explain why sine of 2 theta is negative for this range. And when we have 2 theta, we have sine of 2 theta. The way this looks on a graph is that the theta would be sort of twice as quick, or for instance, sine 2x, which I'm more familiar with, would be the x is going 2 times as quick. So we have our 1, 2, 3, 4. We have our 1 and -1 like that, respectively. So the graph would still start at 0, but it would go much quicker. In the way that a normal graph, 1, -1, notch, 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 it would go 0 to 1 to 0 to -1 to 0. It would do that 2 times as quickly. So in the time that it would take to go from 0 to 1, it would go already back down to 0 like that. And it would go back down to -1 like this. So in the time it does 4 things, it would do 2 things. So pretty much what it's saying is that instead of going like do 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 do, it's going like do 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 do. And with the knowledge that the cosine of theta equals k, we're just going to assume that k is a positive number, right? So we're taking the cosine of a positive number. So it would originally be this, but now we're going to do 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 do, and we're going 2 times as quick in the same range. So we're going to end round there. You know, it's a very vague estimate. So for answer explain, that's words, and we have 2 marks, so it's probably 2 things you're supposed to say. One thing I would say is that theta is in the, you could say 3rd or 4th quadrant. Actually, is it? I don't know if it can be in the 3rd, because that would imply k is a negative number. So right there. Well, sine would still be negative, so I think that's a decent answer to say theta is in the third or fourth quadrant. I think that's good enough to have. But then you're taking cosine of a negative number. So actually, it could only be in the fourth quadrant. My bad. Because let's say k is 3. I'm just going to toss a... No, it has to be between 0 and 1. So we'll say it's 1/2, right? So cosine of theta of 1/2 would be in this quadrant or this quadrant, the A or the C, the first or the fourth. But on the other hand, if it is a negative, it would be on these two. So, and we know for certain it cannot be in sine. So I would say that it's in the fourth quadrant because it needs that double answer as well. So the theta is in the fourth quadrant. That was probably one of our marks, just say that it would be there. And I would also make a point that it's between 540 and what's 360 times 2? 720. Okay. So 720. I could probably draw this so it's more clear. So we have 540 and 720. And the reason why I'm not writing 0 to 360 is because we're going all the way around and we're coming back again. So I would write a line saying it's between 540 and 720 because that shows you truly understand what 2 theta means in this context. Sine of 2 theta. It's okay if you don't get these. The word questions, I'd say, are some of the hardest questions because that's where you truly have to think about the problem. You have to understand some underlying concepts, and those stump me all the time. So let's say theta is in the fourth quadrant because it's between 540 and 720, comma, and sine is always negative in that region. That's generally the estimate of what I would write. And that is it. That's probably our 2 marks right there. So thank you for watching. It means a lot to me. If you have any suggestions, recommendations, let me know down below. I'm open to doing more chapter 5, doing more whatever. Just let me know and have a good one. Bye.